So this is the banked turn assessment. In this situation, we have a car going around a racetrack with a radius, a circular racetrack with on this turn, and the turn radius is 150 meters, and the bank angle of the turn, because it is a banked turn, is 31 degrees. The first step of this problem is to draw a force diagram for the car trying to drive around the turn at a speed so they don't need to turn the steering wheel at all. And we're going to represent the car as a point. We have the earth pulling down on the car, which is mg. We have the normal force perpendicular to the surface. So this is going to go out at an angle of theta relative to straight up. That's our normal force. And the two component forces of this normal force are our normal force in the y direction and our normal force in the x direction. And so that's it. That's all the forces we have in the car. We have the normal force and the mg. First question is, how fast could the car go around the turn without turning the steering wheel and stay in the same lane? So in order to do this, we need to work out the x. We need to, if the car is going to stay in the same lane, we know that the net force in the x direction, we need to do something with that. So we're going to work out some F net statements. First one we're going to do is F net y. F net y is 0 because the car is not accelerating up or down. And F net y also is ny minus mg. And since F net y equals 0, we know that the normal force in the y direction is going to be equal to mg. Awesome. Next step is think about F net x's. So our F net x, since we're traveling in a circle, is going to be equal to mv squared over r, the centripetal acceleration. And F net x also equals our normal force in the x direction, nx. So we can set these two equal to each other. We can say nx equals mv squared over r. Next step, we want to relate our ny and our nx, and we can use a tangent of our bank angle to do so, because tangent is opposite over adjacent. So we can say tangent of theta is going to equal ny, or nx, I mean, nx over ny, which will equal mv squared over r over mg. So our m's are going to cancel out. We're going to get tangent of theta is equal to v squared over rg. We can rearrange this to say v squared equals rg tan theta, or v just equals the square root of rg tan theta. We plug in all our numbers, so v will equal the square root of our radius, 150, times g, which is 10, times the tangent of 31. And so we're going to get a v of 30 meters per second. That's how fast the car can go without turning the wheel and not move out of its lane. Next question we have is, at 30 meters per second, so at 30 meters per second, how many times heavier does the driver feel? So in order to evaluate this, we know the way the driver feels is the ratio of the normal force over mg, because normally when you feel the normal weight, this is the normal force over mg, it's the same number, and that's just 1. So you feel 1 times heavier, so you feel normal weight. But if the normal force was twice mg, you'd feel 2 times as heavier. So we want to focus on this ratio. and we want to find our normal force. From the previous step, we know our normal force in the y direction was equal to mg. We also know our normal force in the x direction was equal to mv squared. So we can use the Pythagorean theorem, because this is a right triangle, to find our just straight up n. So we can say n squared equals nx squared plus ny squared. We're going to substitute in our mg, or our mv squared over r, and our mg, and then both of these guys are squared. We're going to work this out further. N squared, or we're going to start plugging in our numbers. So we're going to say n squared equals m 30 squared over 150 squared plus m squared g squared. So n squared will equal 36 m squared plus 100 m squared. N squared equals 136 m squared, because this is same term. We're going to do the square root of both sides. N will equal our m, or n will equal my bad. N will equal 11.66 m squared. So that's our n. We can plug this into our ratio to figure it out. Or no, not m squared, just m. So we'll get 11.66 m over mg, and we know g is 10, over 10m. So we're going to get m's will cancel. The driver is going to feel 1.66 times heavier. All right, great. Next question is, in the best possible conditions, the coefficient of friction between the track and the tires is 1 Newton per Newton. How fast could the driver take the turn under those conditions? So big thing is changing here. We're adding in friction. This is huge. We got to redraw our force diagram. Forget our speed before. We now have a friction. And our friction is going down the track, parallel to the track, in fact. And we have a component vectors for the friction. We have a f of x and then a f of y. So we got to recalculate our f net x and our f net y's now that we have these frictions messing with it. So we're going to say f net x. I'm going to do it here. F net x equals mv squared over r, centripetal force, as we said before. But it's also going to equal the f of x. Let me do that in green. F of x plus n of x. And we can't really do anything with just fx, nx. So we want to put this in terms of our straight up f. Another thing to add, this green angle here is also theta. Just the way the geometry works out. Next thing we want to do is say f net x is equal to f cosine theta, because f of x is adjacent, f cosine theta plus n, and the x is opposite from our theta, n sine theta. So we use cosine here because it's adjacent to the theta, and then we use sine here because it's opposite from the theta. And then we can say, of course, substitute mv squared in for f net x. Mv squared over r will equal f cosine theta plus n sine theta. So that's great. Now we want to do y's. We're going to say f net y is 0, right? We've said that before. We'll say it again. F net y is 0. The car is not moving up or down, or accelerating up or down, I should say. So f net y, if we look at forces, is equal to the ny, which is up, minus the f of y, which is down, minus mg. So we can say, you know what? Hold on. Oh yeah, we want to substitute in workable solutions for that. So we're going to substitute in f net y equals ny is adjacent to the angle, so we're going to say f cosine theta, or n cosine theta, my bad, and fy is opposite of that theta, so we're going to say f sine theta, and our mg is still just mg, right? So we can say mg is going to equal n cosine theta minus f sine theta. Now here's an important thing. We're going to use our coefficient of friction. They told us it equals 1. Mu equals 1. So we know mu is equal to f over n. So that means 1 is equal to f over n, which means n is equal to f. So everywhere we have n's and f's, we can treat them as the same thing. Just use the same variable. It makes it way easier to solve. And actually, we need that to solve this. So on this side, we can say mv squared over r is equal to, we're going to replace this n with a f, and then we'll factor the f's out. So we can say f cosine theta plus sine theta. And then in the y half, we can say mg, we can substitute in an f for this n, and we can say mg here equals, factor out that f, mg equals f cosine theta minus sine theta. So now we want to take these two equations and find a way to kind of put them together, right? So we're going to solve for f in the y. I'm running out of space, so I gotta erase this, but we're gonna solve for f in this equation here, and we're also gonna solve for f in this equation here. So if we solve for f here, we're going to end up with f is equal to mg divided by cosine theta minus sine theta. And if we solve for f down here, we're going to get f is equal to mv squared over r, or we can just say mv squared over r cosine theta plus sine theta. So now we have two equations for f, and we can plug this part into there or this part into there. We can substitute it in. So we can say that mv squared over r cosine theta plus sine theta equals mg over cosine theta minus sine theta. We have an m on both of these sides. I'm going to get rid of it. And then if we cross multiply the r cosine theta plus sine theta over to the g, we can get v squared is equal to this big old fraction, which is rg cosine theta plus sine theta over cosine theta minus sine theta and then we can, if we were to square root this whole thing, I don't want to write it out again, so we're going to say v is equal to square root of that whole thing. Then we plug in all our numbers, right? We'll get v is equal to the square root of r, 150 meters, g, 10, cosine, all the thetas are 31, so sine 31, over cosine of 31 minus sine of 31. And we plug this whole big bad boy into our calculator, we'll get a v of 77.5 meters per second. Which means that when we're going around this track with an angle of 31 degrees, a radius of 150 meters, and a friction coefficient of 1 Newton per Newton, our speed, the driver can take the curve, is 77.5 meters per second.